All right. So I think we'll move on to talking about some open problems. Yeah, this is not meant to be an exhaustive list, but these are going to be the ones that seem to keep coming up in our discussions. So it's maybe worth making a list. So I'm going to put the list in context by making the following statement, which is that deep learning theory is stuck because people are impatient. Now, that's not the only problem in the field, but certainly I think it is one of the problems. But we are patient.
So should we tell Susan how to attach this?
Oh, sure. Yeah. Sorry, Susan. I should have given you a bit of a heads up how things work. So, the easiest way to listen is to if you see this orb up here at the front, this kind of ball on the ground.
Yeah.
So if you walk up to that, you'll see a little prompt near your feet which says "attach as listener." Do you see that?
Yep.
Okay. So if you hold down E or just click it and hold, you'll.
Oh, got it.
So now you should hear me more clearly, and if you click OrbCam up the top of your screen, you'll get a view of the boards. That's kind of a convenient way to look at things. So this is
I see.
how
Got
people
it.
are often watching.
How do I go back to muting myself when I'm in this orb cam?
Yeah, unfortunately you'll have to go out of OrbCam, mute, and go back in. Sorry.
Oh.
Unless you got a hotkey, I guess.
Yeah, we can't hook a hotkey into the mute yet. They haven't. That's not possible.
Yeah.
Unfortunately. Yeah, that's a highly desired feature. Okay, we're patient. Now that's one way of saying long live one layer tanh.
Oh, just curious, like, will the contents of the board be available, like, or should we, like, should I be taking notes, or
There'll be a
will
video
there be
recording
copies?
that'll be posted. The boards, there's no way to export them currently as like a PDF. But yeah, so the video is the accessible thing outside the world, and these boards stay here, so you can always follow that link. That link you used to get here will always point to this place, and the boards will always have whatever they have when I finish.
Oh, great. Okay, got it. Thanks.
Yep. So the first series of problems I'm going to list are problems, they're sort of general theoretical problems, but the kind of test case in which to study them is one hidden layer tanh. And there's no shame in thinking about one hidden layer tanh. So we understand this case well. Well, we don't completely understand it, but we understand something about it. And there's still a lot of value to be gained from thinking more about it. I think we shouldn't be in a hurry to move beyond it, although obviously eventually that's what we aim to do. I think one should be not afraid to be patient and just steadily work through this very central and basic example. So with that context, so the following list of problems sort of refer to one hidden layer tanh. They're not in any particular order. So the first one I'm going to list is to systematically apply toric methods. So toric methods means toric varieties, or toric ideals. This is a part of algebraic geometry. Toric varieties, I won't give the definition, it's not really the place to do that, maybe some other time. So toric varieties is a kind of combinatorial part of algebraic geometry. Toric varieties are easy to resolve in the sense of resolution of singularities, or at least the resolution process has a kind of combinatorial flavor. It's sort of can be visualized in terms of polyhedra and subdividing faces and stuff like that. The varieties that arise as sets of true parameters in one-layer tanh networks are toric varieties, or at least can be treated by these methods. So there's an opportunity to kind of systematically adopt this point of view to redo and perhaps extend what Aoyagi and Watanabe did to compute RLCTs of one hidden layer tanh networks. And I think this is an excellent exercise to do as preparation for going beyond one layer. So if we want to understand deeper tanh networks or other nonlinearities, I think getting a really solid grasp on this part. We sort of understand now, modulo some details, how to go from analytic to algebraic for one hidden layer tanh, and that's great as a result of Spencer's thesis and work that Matt has done and work Edmund has done. So that's part of the story, but there still remains, I have not read and understood the Aoyagi Watanabe paper. And I don't really want to read that paper either, because I'm not convinced that the way they're doing it is kind of the most elegant way. So I think we should find the high road to resolving the singularities of one hidden layer tanh networks. And I don't think that's currently in the literature. And these toric methods should be more general than this example as well. So feel free to ask questions as I go through this list, and we can go back and add details and jump around, but I'll just proceed if nobody asks me questions. The second is one that we've discussed, but we haven't resolved yet, which is renormalizability in the precise sense of the asymptotic learning curve paper that Edmund was speaking about a month or so ago. So the renormalizability condition for one layer tanh networks. I guess it's, as I said, all of this is implicitly kind of do it for one layer tanh and then see what we can learn to do more general cases. This is the unrealizable case, obviously. Okay. 3. Phases and phase transitions. We're interested in this for varying true distributions, phase transitions that happen as n goes to infinity, and I want to put here other limits. And maybe I'll add this as the next problem. Other limits, not just n goes to infinity. I was talking to Liam yesterday, Liam Hodgkinson, who's a new faculty member in our school, and he was pointing out that in his point of view the n goes to infinity limit is the wrong one. I'm not sure I completely agree with him, but certainly we do believe that it's interesting to consider limits that look like, for example, the ratio between the data set size and the number of parameters constant and taking both of them to infinity at the same rate. So this kind of limit where we're varying the number of parameters, we really haven't thought about at all. And this is, I think probably quite important in understanding. Well, we're not sure that the limit that we've studied, the n goes to infinity asymptotics, are really the ones that are relevant to deep learning theory. It may be a helpful starting point, but it may not actually. We might be distracting ourselves by not considering other limits.
So this n and d both going to infinity, that's quite at a certain ratio. That's quite a common asymptotic regime in statistics. The traditional one is just n going to infinity with d fixed. But this is also it's also very interesting and probably more relevant. There's also like the d going to infinity with n fixed regime. These are kind of the three asymptotic regimes that are considered. And then both of these going to infinity kind of has this like almost like a random matrix theory flavor to it. But yeah, I don't think Watanabe has considered at all this n and d both going to infinity.
Yeah, do you have any feeling about? So Liam's point of view seems to be quite strong, that he's just convinced the n goes to infinity limit d fixed is just not interesting. I'm, I suppose, not convinced.
I think that
but
that is somewhat valid because I mean we want to use these asymptotic results to inform what happens in the finite case, and if your practice is such that d is much larger than n, then it's not clear large n asymptotics really buy you a lot, because the behavior will be quite different to the limiting result you get when n and d are both going to infinity. But I haven't seen that many analyses of this n and d both going to infinity. Maybe we can ask Liam for some examples of people doing this in deep learning successfully.
Yeah, I think that'd be a good idea.
Isn't lambda the new d anyway in SLT?
Yeah.
I mean, it's hard to send lambda to infinity when the first three, well, I don't know, the first one or two open questions are how to calculate the damn thing in the first place. But
yeah,
it seems like n over lambda is enticing.
Yeah, I guess you could say... Oh, sorry, go ahead.
There's a point that, so it depends on what we... I think it crucially depends on what do we mean by increasing d. For example, are we adding... So if in the one layer case, that's kind of very clear, it's just add more nodes. But it seems like the relationship between d and lambda is such that how you add extra modules, like if you are adding an extra transformer block, attention block, versus adding an extra fully connected layer, I mean that changes lambda in very different ways. So yeah, so it does seem like the correct. Mm-hmm.
I think that was an echo of your own voice, Edmund.
Oh, okay, right. Yeah, it does seem like D might be the correct thing to increase, but if we almost want the resulting expression to be lambda as a function of D or something like that.
Yeah, I think you're right that it does make a big difference whether you send the width to infinity or the depth at fixed width to infinity. So we know from some of these universal approximation results that roughly speaking, if you keep the width to be something like the sum of the input dimension and output dimension of the functions you're trying to approximate, then you need to make the function deeper as the modulus of continuity of the function gets bigger or larger. I forget which. Meaning that the kind of rougher or the more fine the detail in the function, the more depth you need. So you can imagine that, I mean, I don't know how that relates to n going to infinity, though. You kind of imagine kn getting simpler as n goes to infinity, right? So maybe that connection doesn't make a whole lot of sense, but yeah, it does seem like not any way of increasing d is really the same limit. Different ways of adding nodes or parameters are different limits. Yeah, regarding lambda, I mean, I guess lambda is kind of the codimension, right? Proportional to the codimension. So it's kind of W0 sitting there, and then you have the number of orthogonal directions divided by 2 is the thing that upper bounds lambda. So if you're adding lots of dimensions that don't do anything, then yeah, you are increasing lambda probably, but yeah, you're not, in some sense, maybe in some real sense, you're not really changing the geometry. So yeah, I don't know how to think about that.
While we are in this context, I kind of also want to point out something that I kind of have a thinking area before, which is the problem that we wanted to solve, or the phenomena to explain, is why does deep learning work well for different true distributions, and it's almost like across many true distributions. And I kind of want to point out that lambda is a function of the true distribution as well. Mm-hmm. Yeah. So it seems like there's a lot of subtext hidden in the sentence and d going to infinity.
Mm-hmm. Yeah, I'll just add that this renormalizability condition is needed for the sort of power law discussion, or at least in our current point of view. Cool. Okay, I'll move on to the next problem, I guess, unless there's further comments about those four.
Is the renormalizability condition for the renormalizability for the realizable case, like, understood? Is that why you wrote?
Realizable implies renormalizable in this definition, yeah.
Yeah, okay.
So the question is only a question in the unrealizable case, yeah. So problem 5 is SGD versus the posterior for one layer tan H. This is something that really we should have done some time ago, I guess. One could do this for much more complicated models, but even for one layer tan H, I don't understand what the relationship is between SGD, GD, and the Bayesian posterior, even in very simple examples. So I feel like there's a kind of systematic study of this that is a kind of foundational thing that needs to be done at some point.
Edmund, don't you have some empirical results on this where you just took like a two-dimensional one layer tan H and looked at, you know, the behavior of SGD as like a process versus
I have empirical. Yeah, so again, it's no, again. So it's more like the Langevin path instead of SGD part, so there's noise artificially injected in that, and it's more like I have empirical plots of trajectories, but and I can say that they are affected by singularities, but and obviously the sort of the RLCT, the kind of things RLCT encodes, like the codimensions and things like that, does affect behavior of the Langevin gradient descent dynamics. But beyond that, beyond saying that, yeah, it obviously changes. I don't know how it changes. Yeah.
But I mean, there should be some way to verify empirically if SGD, or take a simpler version of SGD, your Langevin process, like if it's a good approximate sampler from the for the posterior. Like if you just run SGD many times and just keep track of where it ends up to a scatter plot and see if that looks like the two-dimensional one-layer tan H posterior.
Yeah, an even simpler thing that I don't know the answer to is, what if you just graph test loss against n? I mean, what does that mean exactly for SGD is a little unclear, but you train for some fixed time and then if SGD looks like the posterior, then you might expect that. And there's a whole bunch of question marks around the relation between. Okay, maybe we should just step back a minute and explain why this is a basic question. So, and an important question for any application of SLT to deep learning is, we have various quantities in SLT like Bayesian generalization error that we have theorems about, and we know asymptotics as n goes to infinity. Well, it could be that those results just have nothing to do with deep learning at all, because the n goes to infinity limit is the wrong limit, and the Bayesian generalization error is the KL divergence between the truth and the predictive distribution, but that's just irrelevant to the test loss, which is what people mean by generalization error when they're actually doing experiments in deep learning. So to make these connections, we either have to suss out which parts of that need to be replaced by, say, other limits or some other kind of theory, or find ways of justifying these connections. But we really are missing even the basic planks in that, just testing basic propositions. So I don't know, for example, even if you just kind of graph test loss against n, does that look like something over n or not? Does it look like something over n to a power or not? I don't even know. So, Edmund's been working on this. So I should say that many of these questions are things that we've discussed before, and in various combinations we're working on various subsets of these. So it's not like these are completely virgin territory, but I don't think we've answered any of these yet. Did you want to say more about this one, Edmund?
No, except I should get on just running those experiments.
Yeah, well, that wasn't quite.
So Edmund, I think Liam Hodgkinson might be a really good person to talk about. Just setting up some good experimental settings.
Yeah, I think just even for now, like the experiment you just suggested and the other experiment, which is so plotting SGD test loss against D, so increasing D, but somehow fixing lambda versus increasing lambda flat out. So the idea is that test loss should decrease as lambda decreases, not as D decreases, and that's kind of a evidence that the singularity is having effect on SGD, which is like no one dispute that. I think, and sort of the Amari natural gradient, like people has known that since a while ago, but maybe sort of a direct influence of lambda RLCT might be interesting. But yeah, I have in my to-do to talk to Liam.
Yeah, I think he's a smart guy, well worth talking to. So the sixth problem is power laws. So trying to understand the possible kind of medium n behavior, I suppose. So we know that as n goes to infinity asymptotically for a renormalizable model, that the Bayesian generalization error looks like lambda on n. But there's a sense in which maybe we can believe in a kind of emergent learning curve that looks something like lambda on n to the gamma for some gamma that's not equal to 1. And there's a question mark whether this is related to the power law behavior that people see in training, say, transformer models. So what I'm proposing here is not to understand it for transformer models, that's too ambitious. But we've discussed modulo some of these considerations I was just pointing out with SGD versus the posterior and so on. We sort of maybe have a bit of a lead on understanding how to think about power laws with exponents different to 1 for one-layer tanh networks, subject to various other things being resolved. For example, the renormalizability condition, and replacing some upper bounds for kind of energy and RLCT for these other phases by kind of upper bounds and lower bounds or equalities. So there's a bunch of question marks here, but this in the category of things that understanding it for one-layer tanh networks would be hints towards good directions to pursue more generally. This seems high on my list of importance, as we have discussed before. Okay, that was it for one hidden layer tanh networks sort of problems oriented towards that. Did anybody want to add to the list? I've got some more general things. Anybody want to add to the list to problems that are kind of specific to one hidden layer tanh? All right. So let's see. Other problems, deeper networks, other nonlinearities. I could add somewhat embarrassingly to that list biases, which is an open problem in SLT, unless Spencer was busy and didn't tell me. Is it solved problem, Spencer?
No, not yet. I've done a little bit sort of following on from that suggestion Matt had a little while ago, which looks like it could be useful. I should, try and write some stuff up for that.
Okay, that's clear then that Spencer has solved this. So
it's not solved.
So deeper networks, so deeper tanh networks is completely open. There are some upper bounds for the RLCT stated in one of Watanabe's papers. I'm not sure any of us have really understood to what degree they're justified. in that paper. I don't know if that's your state of knowledge as well, Edmund. I kind of buy maybe what he's saying there, but I'm far from understanding it, and I think it's not close to being. It's really just an upper bound, probably a rather coarse one. So I don't think at the moment there's really a clear idea how to do deeper networks. I'm hopeful that if we were sitting here really understanding how to do one hidden layer tanh with the toric methods, that how to progress to deeper networks might seem somewhat routine, but that isn't the case. Obviously, you might say, well, okay, we're going to do 1 layer and then 2 layer, and then every 4 years we'll increase the number of layers. That would be a bit futile. But that isn't what you'd hope to get out of this exercise. You'd hope to understand how to do each additional layer by somehow, with some technique, reducing, more or less hoping the work is mainly in the 1 hidden layer tanh case, and then a kind of inductive step where you really only have to do these 2 parts. You do 1 hidden layer and then going from n to n plus 1. That would be the ideal. I don't know how realistic that is.
Can I ask a very naive question about 1 layer tanh networks?
Yeah.
That just occurred to me. When all these problems that we're doing, have we typically picked a P, Q, and W? I think the true function is assumed to be 0. And is there an assumed posterior and an assumed distribution for the posterior and P and Q?
You mean prior, perhaps?
I guess canonical prior. Sorry, yeah.
Yeah.
Canonical ones that.
Yeah, the
most
prior.
of us are done with.
The prior kind of gets chosen to be whatever it is that makes the mathematics tractable. But
okay.
Often it's not crazy things. I don't know. Maybe you would disagree with that, Spencer, but.
Yeah, I think with what I was doing, I was just I think what Anavi's done is just have a uniform view on some finite length.
At least in terms of the approaches we've taken to, for example, replacing the KL divergence by an algebraic function, the choice of prior can be quite. It's not a small thing. From some point of view, as long as the prior is positive on W0, it doesn't matter to the asymptotics. But from the point of view of actually finding the equivalent polynomial, it seems like it makes a big difference, or at least the mathematics looks rather different. The integrals you do could be tractable or not, depending on the form of the prior. So it seems like it both matters a lot and doesn't matter at all. So I don't know quite how those two fit together. Regarding the true distribution, that makes a difference, yeah.
Okay, thank you. I was wondering if it was a Gaussian that everyone knew and I just didn't.
That would be a natural prior to choose, except that for other reasons it's very useful to take the domain in which your inputs live to be compact. So that rules out taking a Gaussian, yeah. Other nonlinearities, so one could try things like swish. I guess that was also on Spencer's to-do list at some point. I don't know how hard that will be. That seems unclear. Why would one care about other nonlinearities? Well, nobody actually trains neural networks with tanh, so that gives the results on tanh a kind of antiquated feeling, I suppose. From a theoretical point of view, a mathematical point of view, it's not clear to me that deep phenomena are really so dependent on the nonlinearity, and so maybe it's not too important, but it is certainly something that if you could get it to work for Swish, then it's pretty close to ReLU and therefore maybe looks more serious. So I think it's worth investing some effort in. I don't know how different the mathematics looks when you have the Taylor series expansion of Swish as compared to tanh. Maybe it's not so hard to adapt what we did to Swish, maybe it's very difficult. Yeah, thanks, Russell. I'll see you next time. Okay, so 2. Jet schemes or arc schemes. So some of these problems are more in the direction of here's the kind of thing an algebraic geometer would want to think about. So it's not really accurate to say it like this, but roughly speaking, you can think of jet schemes and arc schemes as being a way of understanding the singular structure, which is a bit more tractable or packaged in a different way than the full resolution. And my intuition is that so if you look at the Balasubramanian paper that a few of us are familiar with, I forget the title.
Something Occam's razor.
That's right. It's got Occam's razor in it. Yeah. Okay. That's enough. Thanks.
Statistical inference, Occam's razor, statistical mechanics on the space of probability distributions. So a mouthful.
Yeah. Thanks, Edmund. So in that paper, there's an asymptotic expansion for the free energy, which has the familiar first 2 terms that we know from, say, BIC, and which are reproduced in the WBIC. But there's higher order terms in the regular case, possibly also in the kind of minimally singular case, or whatever we want to call it. Probably still works. I'm not sure. But certainly in the regular case, you can see higher order terms which have a geometric content. So they have an interpretation in terms of curvature and so on. And my impression is that you could potentially do something like that in the singular case by making use of more sophisticated ideas from jet schemes. Arc schemes is just another name for jet schemes. So this would maybe give a geometric interpretation of some of the terms that are kind of hidden in the OP1 in the current way that we write those formulas. I don't know how much we care. Like as from a geometry point of view, it's interesting. From a statistical learning point of view, I don't even know that anybody cares about the higher order terms in Balasubramanian's paper. Someone can correct me if I'm missing the plot there, but it just doesn't seem that important. So maybe this isn't. It's not obvious to me it's important from the point of view of the application to statistical learning theory, but it's kind of a geometrically well-motivated, like pure mathematically interesting question. So I think I like it. Yeah, this is a kind of line of investigation that I started with James Clift and Tom Waring and James Walbridge, which is kind of sitting there waiting for a bit more attention. Which is there's a kind of potential for a dictionary between. So Watanabe is saying in the introduction to his book that knowledge is knowledge to be learned from data is a singularity, and we sort of understand to some degree what that means. But the knowledge that's to be gained from data is increasingly well viewed as an algorithm, right? Now, maybe in classical statistics, that's not how you would think about the parameters that you learn from data. They're parameters in a model that is the way it is. But if you're learning a neural network, then maybe the neural network encodes, well, certainly does encode an algorithm, but maybe that's a good high-level way of thinking about it. So, for example, there's increasing evidence that the algorithms that are learned by transformer models are interpretable. So you can look at the weights and see, oh yeah, okay, so it's basically doing this. And the this is a list of operations that you would understand as an algorithm that a human might execute in that context to perform that task. Now, the algorithm is represented in some list of weights, but it's not just some crazy linear algebra that has no clear, like, symbolic content. One should be careful reading too much into these things potentially, but as time goes by, it's becoming more justifiable to think about the results of learning in some of these large models as being algorithmic in character. Okay, so how seriously to take that connection between algorithms in the sort of classical computer science setting and the singularities that are the knowledge that is learned from data when the model is a neural network. And so one way to investigate that connection is to find a way of embedding both worlds into the same place. So what we did with what Tom Waring did in his thesis, for example, was explain how to go from a Turing machine, use it, or rather a code for a Turing machine on a universal Turing machine, how to use that to produce a learning problem, a synthesis problem, such that the original Turing machine corresponds to a point in W0 of that model, so a singularity of that analytic or algebraic variety. Now, and we understand the structure of programs, like we know what subroutines mean, we know what composition means. If we can understand what those structures on programs mean at the level of singularities, then it may give a dictionary for talking about the kinds of algorithms that we learn in neural networks. So this programs of singularities idea is a way of bridging the old world of programs, Turing machines or code, with the new world of programs, algorithms that are inferred from data. So this is not a specific problem necessarily, but there's a list of problems associated to this that are in this PAS1 and PAS2 are a pair of handwritten notes that some of you have. And if you're interested in that, I can say more. That's sort of relevant to the earlier discussion about phase transitions. So there are some very interesting plots if you look at the recent output of Anthropic and Chris Olar's group. There are some very interesting plots where they show, as they train small transformers on kind of algorithmic tasks, there are clear phase transitions when these algorithmic structures appear in the weights. So there's a very interesting, potentially quite deep link between phase transitions and the emergence of kind of symbolic algorithmic structure in these systems. And ultimately, this is kind of the reason I care about phase transitions. And maybe I'll list one more. Which is again an area of investigation rather than a specific problem like the earlier ones, which is renormalization versus resolution of singularities. And this we've been discussing in the abstraction seminar, so maybe I'll just defer to that seminar for future investigation of that topic. Right, that's all I had. Edmund, what would you add? Susan, what would you add?
I have one technical one, which is what happened for non-renormalizable and or even non-essentially unique cases. We have kind of a partial answer in one of the paper by Watanabe for restricted case.
Right. Yeah. There's also this cryptic comment about symmetry breaking in Watanabe's work, where he says, "This will be very important," and then that's the last we ever hear on that topic from him. Yeah, no worries, Susan. I can, if you have problems you want me to add to this, I can come back and put them in here later. Yeah, that's a good one. That's kind of a question about how universal the equations of state are, I guess, right? Like, what is the proper class of models? Is that right?
Yeah, speaking of that, so a more conceptual one would be put a little bit fast and loose, is what on earth is the equation of state? But so less flippantly, what is the connection between learning systems and thermodynamics and statistical physics?
Yeah, that's a good one. Yeah. Let me say thermodynamical dictionary. I'll just clarify that with singularities, because of course there is a dictionary that relates statistical learning theory to thermodynamics, but from our point of view, it's incomplete. Susan says she's going to maybe present some problems to do with variational inference in SLT later. That would be excellent. Yeah, thanks.
I think there is kind of a broader heading, which is, I guess, translational work, as in how does the knowledge about singularities in learning problem, how does that translate into improving algorithms and so on. So the variational inference, like how do we use, so like Susan's work has that flavor of, now that we know singular models have so and so structure, and it seems like knowing that could improve algorithms.
Mm-hmm. Any more or other questions people want to ask about the problems we discussed earlier?
Is the thermodynamical dictionary like the link between statistical mechanics and SLT?
Yeah, this.
I saw that in Liam's thesis.
Yeah, if you refer, yeah, it's in Liam's thesis and it's in some of my notes, but this is an old topic. I mean, people have been applying statistical mechanics to learning theory for many decades. So it's certainly not something we came up with. However, that link has kind of overemphasized what we would call the regular case, right? Where there are, that's what Balasubramanian's paper is about, for example. This is an exposition of that linkage, which is not invented by him, and he's adding to it in some ways. But a lot of that has presumed the regular case, and so suffers in the same way as much of this does from a lack of attention to the singular case. So there's still open questions about how to think about this dictionary. I would say even in the regular case, I'm not convinced that people really have thought through completely, like what, or at least I don't understand how to think about everything I know in thermodynamics that seems appropriate to translate, how to think about that in a learning theory context. So maybe there's work to do even there, but certainly in the singular case, it's we could probably do a whole seminar on just what we don't understand. That's kind of in the singular case specifically. Yep. That goes the other way as well. That's kind of what maybe that could go under the heading of what Edmund just said. So there are various things in physics that you could just see from the point of view of SLT. You could think about them in a more refined way, which is maybe a way of saying that everybody should bow before Hironaka and study his works. Yeah, maybe it's worth separating out as a separate. It's worth separating out. Well, maybe I'll just add as an item under number 3 is. There's almost certainly improvements that can be made to Markov chain Monte Carlo, or like you could imagine some kind of form of Hamiltonian Monte Carlo that pays more attention to singularities or something. Okay. Yeah. Any other comments or problems people want to add? This world will stay here, and I have in mind that we'll come back and add to these lists and discuss them. So this is not meant to be the final word on this list, but the beginning.
And you left some space to explore each one for the solutions.
Yeah, that's right. Well, I've left room for the archive numbers as we solve each and every one of these problems. Okay. Yeah, if there's nothing further to add at this time, then maybe we'll wrap up. Yeah, thanks everyone. And I think next week, Edmund, what was the plan for next week?